Hello, welcome back. This is Terry Collins. The title of this lesson is The Bookcase of Green Chemistry Problems Part 2. In this lesson, we'll discuss the difference between design for and design against shelves on our bookcase analogy of green chemistry challenges. We will examine the major classes of green chemistry challenges that fall on the upper three shelves of the bookcase, and we'll outline why and how green chemistry and the environmental health sciences should be united. This will give us an example, perhaps the best example we could choose, of how green chemistry must align with other critical areas of science in order to meet its challenges of reducing and eliminating hazardous substances. Now let us consider some details of the bookcase analogy. Remember from Lesson 1, Module 2, that human sustainability determinants are drivers we control that influence the natural determinants that govern whether or not our civilization will be sustainable. For any green chemistry project on any shelf, it may be difficult to orient any particular human determinant to promote sustainability in the natural determinants affected by the hazardous product or process. Usually the underlying reason is the expense, the cost of making a change. In the previous lesson, we examined the lower three shelves in the bookcase of green chemistry challenges. We called these the design for shelves. There's a reason for that. Problems on the design for shelves enjoy an advantage over problems on the design against shelves. Green chemistry approaches on the design for shelves usually promise enough economic opportunity to promote research and development work that has the potential to move one or more natural determinants to favor sustainability. Now we'll consider the upper three design against shelves, where incumbent products and processes often represent substantial health or environmental risks, but where the economic incentives for changing to a green product or process are hard to identify, and economic disincentives associated with change are all too obvious. The idea that a problem on one of these shelves should be solved expeditiously may meet with substantial resistance from one or more of the human sustainability determinants, making it much harder to carry out the research and development needed to orient the affected natural determinants towards sustainability. When it is difficult to get any particular human determinant to align towards sustainability, other human determinants can compensate by orienting all the more definitively in the direction of sustainability. The importance of education as a flexible human determinant is obvious in this analogy. So now let us examine the fourth shelf coming up from the bottom on our bookcase, design against toxic elements. One of the major reasons that chemical products and processes can be toxic is that in their constitution we have come to use virtually the entire periodic table of elements. So in reaction chemistry, chemists developing new processes strive principally to achieve reactions that only produce the desired product. This selectivity, as we call it, is achieved by using relatively simple reagent designs and employing almost the entire periodic table to attain diverse reactivity. In contrast, nature accomplishes a huge range of selective biochemical processes, mostly with just a handful of environmentally common elements. Selectivity is achieved through a reagent design that is much more elaborate than the synthetic one. For example, electric eels can store charge via concentration gradients of biochemically common alkali metal ions across the membranes of electroplaque cells. In contrast, most batteries used for storage require biochemically foreign toxic elements such as lead and cadmium. Because of this strategic difference, man-made technologies often distribute throughout the environment persistent pollutants that are toxic because they are elements or they contain elements that are used sparingly or not at all in biochemistry. Wherever we are using these toxic elements in any technology in any product or process, there is a green chemistry challenge. So for example, lead and NiCad batteries, nickel-cadmium batteries. Those energy-efficient fluorescent light bulbs that we are all now buying to replace the old, much less efficient incandescent bulbs contain mercury vapor that is excited electrically and in turn excites a phosphor on the glass surface that then gives out the light. When you break one of those fluorescent light bulbs, you put an amount of mercury into your local environment, thus prescribing a green chemistry challenge. The chalcogens are one family of chemical elements, one vertical column in the periodic table consisting of oxygen, sulfur, selenium, tellurium, and polonium. Soft metal chalcogenides tend to be salts of sulfur, selenium, or tellurium anions and heavy metal cations such as cadmium or mercury. We have to be very careful about their use, which has been growing, because both the metal cations and the selenium and tellurium anions are highly toxic. Arsenic used in agriculture is also a problem. For example, a cotton defoliant, cacodylic acid, is an arsenic compound. If one uses cacodylic acid to defoliate cotton plants, you are clearly going to be placing a lot of arsenic in the surrounding soil. Similarly, we are feeding our arsenic compound roxarsone to some chickens that are being raised for commercial sale, and really we have to question the wisdom of doing this, and if the properties of the roxarsone are so valuable, we have to find safer alternatives. Well, at this point, let's take a book from this particular shelf and open it at the table of contents, the Book of Lead and Sustainability. Here you see topics such as the history of lead toxicity and ecotoxicity, an extraordinary history. Human beings have been poisoning themselves with lead for many millennia. History of lead spin and its consequences. It's an extraordinary fact of history that a small group of people congregated around the Lead Industry Association in the United States kept lead in household paint in this country for many decades longer than it took to get lead out of household paint in other countries around the world. This is an extremely interesting and informative history that should be taught to students of chemistry as well as students of other fields. The biochemistry of lead shows the toxicity origins. We know a lot about why lead is toxic at the very intimate mechanistic details of the toxicity, and this is fabulously interesting and should be presented to students of chemistry. We've made much progress in greening lead products and processes, and we should celebrate that. But there are still many challenges for greening lead products and processes. Of course, the greening of a lead-based product or process requires that the lead be removed altogether. Lead throughout history has had enormous impact on our civilization. For example, lead poisoning may have doomed Beethoven. Locks of Beethoven's hair are available today. They have been investigated for lead. The locks contained 100 times background lead. You're intoxicated if your hair contains 2 times background lead. Thus we can say with considerable certainty that Beethoven was severely lead poisoned. Well, this brings us to the 5th shelf on our bookcase, Design Against Persistent and Pseudo-Persistent Environmentally Mobile Compounds. I use the term pseudo-persistent as it is often used to imply compounds that are being reasonably rapidly degraded in the environment but are being replaced so frequently that a steady state concentration exists in either the environment, an environmental compartment, or in an organism. In this area, we find many of the pesticides are a problem, some of our polymers, but not all by any means, their components and their degradation products, and many of our fire retardants, as well as a wide range of chemicals that are used for different applications. Well, how can we put this in context? One way is to use the following metaphor. Imagine all of Earth's chemistry as a mail sorter's wall of letter slots in a post office, with the network of compartments extending toward infinity. Each compartment represents a separate chemistry, so that, for example, thousands of compartments are associated with stratospheric chemistry or with a human cell. An environmentally mobile persistent pollutant can move from compartment to compartment, sampling a large number and finding those compartments that it can perturb. Many perturbations may be inconsequential, but others can cause unforeseen catastrophes, such as the ozone hole, or some of the manifestations of endocrine disruption that we'll hear much about. Those are represented by the blast that you see there. It's fair to say that most compartments remain unidentified by science, and even for the known compartments, the interactions of the pollutant with the compartment's contents can usually not be foreseen, giving ample reason for scientific humility when considering the safety of persistent mobile compounds. We should heed the historical lesson that persistent pollutants are capable of environmental mayhem and treat them with extreme caution. In cases where the use of a persistent pollutant is based on a compelling benefit, such as with DDT in malaria-infested regions, society must face the challenge of finding safe alternatives. And it's wonderful to see many outstanding scientists working in 2010 on safe replacements for DDT, or better ways to handle the challenge of the Anopheles mosquito that carries malaria and infects people. The last two shelves that we have looked at, Design Against Toxic Elements and Design Against Persistent Environmentally Mobile Compounds, actually intersect beautifully with the principles of the natural step as defined by Karl-Henrik Robert and his colleagues in Sweden and throughout the world. The natural step principles can be worded as followed. To become a sustainable society, we must 1. Eliminate a contribution to the progressive buildup of substances extracted from the Earth's crust, for example, heavy metals and fossil fuels. That's shelf 4. 2. Eliminate our contribution to the progressive buildup of chemicals and compounds produced by society, for example, dioxins, PCBs, and DDT. That's shelf 5. In the assignment section, you are given some reading on the principles of the natural step and the outstanding thinking of Dr. Robert and his colleagues on sustainability in general. The last shelf on our bookcase, the top shelf, involves design against endocrine disruptors. Anything beyond a tentative success for green chemistry requires major victories here. Again, the definition of an endocrine disruptor is the following. An endocrine disruptor is an exogenous substance or mixture that alters function of the endocrine system and consequently causes adverse health effects in an intact organism or its progeny or subpopulations. That's a definition from the International Program on Chemical Safety in 1998. So how then will green chemists learn from the environmental health scientists, the group of scientists who are discovering low-dose adverse effects of everyday chemicals? How will the green chemists learn from them how to design chemical products and processes of the future that are not burdened with these forms of toxicity? To approach this question, we have to map suggested strategies for advancing synergies between the fields of environmental health sciences and green chemistry, aimed, of course, at promoting sustainability. These are the sorts of ideas that come up. We need to evaluate chemistry's and toxicology's strengths and weaknesses for dealing with sustainability challenges. We need to focus on making the most of the strengths and finding ways to overcome the weaknesses. We need to identify and prioritize hazardous substances for reduction and elimination. We need to develop distribution budgets for hazardous substances across marketplace product process profiles. We need to bring environmental health sciences' forefront understanding of hazards to green chemistry design, and green chemistry's understanding of the chemical enterprise dynamics to environmental health sciences. We need to develop a portfolio of assays to ensure that green chemistry products and processes are not hazardous by the standards of contemporary knowledge. and we need to enshrine this assay portfolio in the principle that it must be readily adaptable to new knowledge. We need to test green chemistry products experimentally with new assays and/or screen via quantitative structure-activity relationships to increase confidence that they are not burdened by knowable toxicity. With endocrine disruption, we do not yet know how to do this adequately, and it's vital that we figure it out expeditiously for sustainability. We need to work to level the playing field for green chemistry products and processes by supporting advocacy for regulations where and when appropriate. And we need to work together to defend the science of low-dose adverse effects of chemicals. Environmental health sciences findings of adverse health effects at environmentally relevant concentrations have tectonic significance for public policy. It's not about what might happen in 2030 if we don't act. It is about what is happening now. So as you can tell from this analysis, a great deal of work needs to be done to build essential collaborations between fields to get the multidisciplinary activity that is needed so that green chemists can design new products and processes free of endocrine disruptors. Well, this brings us to the end of our overview of the bookcase of green chemistry problems. In the next lesson, we'll pick up on the endocrine disruption shelf, the top shelf, and consider its contents in a little bit more detail. And then we'll follow that with a lesson on obesogens and the obesogen hypothesis, the postulate that some everyday chemicals could be playing a role through endocrine disruption mechanisms in the obesity epidemic that we are seeing in the United States and in some countries throughout the world.